This video is going to be a little bit haphazard because I'm just pressed for time on this one. But I just wanted to show the moment of rotational inertia to an idiot, basically, who doesn't understand it. But anyway, so in the demonstration, I'm going to show that a 2-mass at one distance has that much rotational inertia. So we've got a 2-mass times 1 radius squared, and that equals 2. Now, when you put half of that mass at twice the distance out, because it goes by the square, so we've got 1 mass at 2 radius, 1 mass times 2 squared equals 4. So even though it is half the mass, it has twice the rotational inertia. So when you've got a given amount of energy and you try and rotate that 1 mass further out, it's harder to move, and that's the whole point of this video, to show that rotational inertia is a real thing, and by placing a 1 mass at twice the distance, it does require more force or more energy to move it, to get it in motion. Here we have the catapult arm. It's a carbon fibre rod and it weighs 22 grams. I'm doing my best here to show the measurements. So from the pivot to where the hook will be, where the spring will be attached, is 16 centimetres. Now measuring from one distance to the pivot point, and again 16 centimetres. Measuring from root 2 to the pivot point, and we have 22.6 millimetres. And finally, oh, there we go, 20, yeah, should be 22.6, it's close enough. And from the furthest one to the pivot point is 32, so twice the distance. So now we have the rod with the bolt through and the hook through. Obviously this is going to add some mass. It originally weighed 22 and we're now up to 31 grams. So it's added, what's that, 9 grams of mass, just adding the fixtures and fittings. So that's the total weight of the catapult arm. The catapult arm, as shown, weighs 31 grams in total with all the fixtures and fittings. So when we're pushing the 500 gram mass, that mass is 16 times heavier, well, over 16 times heavier than the arm itself. And obviously when we're pushing the 1,000 grams, 1 kilogram, that's double, obviously, well, a bit more than double, so that's 32 times heavier. So the masses that are being pushed, you know, are quite considerably heavier. So that's the setup. The camera was fixed above. The 2 masses zip tied together, obviously probably not ideal, but as I see it, as we put it on the one mark in the centre of that, we've got as much inertial mass by the square going down that way, and we've got as much mass by the square going up that way. So if I put it that way, obviously the centre of mass is get further out, and obviously with using the other 500s as singles, I wanted to keep it, you know, in line so it's a fair comparison. Also, these are set so it's pushing because of a weird shape, so I balanced them to get the centre of mass, and obviously it's pushing all of them from the centre of mass. If I used a 1 kilogram weight, obviously it's going to be bigger, higher, its centre of mass is going to be different, and I'd have to mess around doing the setup again. I'd have to higher and lower stuff, where this way keeps everything as fair as possible, as I see it. very free to move without anything attached to it. It's on cartridge bearings. There's a cartridge bearing there, and there's one on the underside, and then it's bolted through.
Alright, so the simple experiment that can be done, okay, is all he has to do, instead of putting a finger here, an unreliable human, just have a spring, okay. Now the spring's going to apply a pressure, and then you're going to release the spring, and you're going to have the lever and the spring, and everything's going to move exactly the same. So it's exactly the same lever, and then you put your 4 pounds here, your 1 pound. Okay, you put your 1 kilogram here. All right, and now you do the test, the contest. Now in this case, the lever, okay, will move exactly the same in both cases. Exactly the same. There won't be any difference at all.
So here we have the catapult system. We've got the plastic board that the masses will be sliding on. That's waxed and polished, as are the bottoms of the masses themselves. Time is starting, all in one take. So we place the 1 kilo or 2.2 pounds at the 1 radius, and we can see there we have motion. And again, and again. Now I'm going to move it to √2 the distance, which will double the rotational inertia, and there we go. It done a move. Because we've hired the rotational inertia, there's not enough energy in the system to get it into motion. We put it back to position 1, and we can see it moves fine. Again, we put it back to √2, and you can just see that moment there where it's like, no, I'm not going anywhere. Put it back to position 1, and again we have motion. So clearly we've changed nothing. We didn't change the mass, we didn't change the mass of the lever, we didn't change the energy going in. All we changed is the position that we're trying to rotate it from, which increases the moment of inertia, and therefore there's not enough energy to get it in motion. So I'm now separating them. We place the 1 mass at √2, and again we get a similar motion to what we saw of the 2 mass at the 1 distance, because now putting the 1 mass at √2 is doubling the rotational inertia, so it's effectively the same as a 1 mass, a 2 mass at 1 distance. So again and again we can see that we've got motion. Now placing the 1 mass at the 1 distance, and it's obviously going to move a lot quicker because we've lowered the moment of inertia. Again, not changed the mass, we just changed the position that we're trying to rotate it from, or the radius we're trying to rotate it from. I swapped out just in case the other one slides better than the other one, so it's a fair test. And again we can see that moves quicker. We put it back to √2 distance, and again we get a similar motion as the 2 mass at 1 distance. Now here's the interesting part. We take one of those masses, the single mass, and we put it at twice the distance, and there we go. It doesn't move. So to say with the same energy input that it'll all move the same it doesn't move the same, because it doesn't move. So what I'm doing now is just sliding it up the lever to lower its moment of inertia, and eventually it will break. It will, there you go. Same as before now, just a slightly better shot, slightly better camera angle. Again, waxed and polished. Got interrupted a little bit at the beginning here, so the timer starts a little bit further on, but the timer is running throughout. So again, the two mass at one distance, and we have motion. We move that same mass, so we're not changing anything, we're not changing the energy input or the mass, we're just changing the position, and there we can see that moment where it just isn't going to budge. Take it back to one distance, and there we go. So when we change the moment of rotational inertia, it requires more energy to get it in motion. And there we go, in motion. Place it back at root 2, doubling the moment of inertia because it goes up by the square. And again, there's not enough energy in the system to get it in motion. As before, we'll separate them. I put tape, on a grey and a white tape, so we can differentiate. So again, when I separate them, I'll use them individually to show if one slides slightly better than the other, just as a fairer test. So there we go, one mass at one distance, and then we swap to the other one. Now one mass at root 2, which again we should get a similar motion as we did with the two mass at position 1. Yeah, it's moving. Obviously I've got no stops on this because it was just to show the moment of inertia, nothing else really. I'll do some proper high speed at some point. So again, one mass at twice the distance, quadrupling the moment of inertia, and it doesn't move. And again, swapped out with the other one, and it doesn't move. Not enough energy there. Put it back to root 2, moves fine. I just wanted to show that because from the video when I watched it back, it does look like that's off the end of the board, which it's clearly not. So it's not lipping over, it's not caught on the edge. So the spring tensioner is just a couple of wing nuts there. Obviously I can undo them and slide this further back, which obviously makes the stop go further back, and therefore when you pull, when the spring's attached, it can adjust the tension, because obviously the start position is further away, and therefore it'll add more, you know, when you pull it, it's got more tension on. The next job will be, I've got a couple of 200 gram masses there, so as before, as this demonstration, I'll use 2 of them. Lower the lever down, obviously, so it's pushing from the centre of mass. Obviously they'll go a lot quicker because there's less mass there. And we can do some proper high speed tests. I need to add some mass to the actual apparatus itself, maybe add some rubber feet, get it up against the stop, and get the camera set up independent, because on the table, obviously when it hit and jolted, it jolts the camera as well. So I'll probably do it on the floor, so the camera setup is completely independent and that doesn't move, and then we can do some proper overlays of high speed and see what's going on, which we already know anyway, but you know, for the goofies out there. So the whole point of this demonstration is just to show that the phenomena of rotational inertia is a very real and physical phenomena. To say that you can launch a 2 mass at one distance and a 1 mass at 2 distances with the same energy, and it will go twice as fast, is never going to happen, which is apparent here. Obviously, this demonstration here, you can see that it is the 2 mass at one distance and the 1 mass at root 2 distance. Yes, I've got no stops on at the moment. I will do that, but this was just to show the moment of inertia, that it is a real thing. It's a physical thing. You can't overcome it. It's just nature, and it's what it does, whether you like it or not. But it's rather interesting, I find, and it was cool to see. So, not perfect because the masses are sliding, but I will, put stops on at some point, lower the masses, and we'll do some real high-speed stuff. But while that end of the lever will move, obviously twice the distance, it will never do it in the same amount of time. As we can see here, to get them to accelerate at the same time, we've got to put it at root 2.
You put your 1 kilogram here. All right, and now you do the test, the contest. Now, in this case, the lever, okay, will move exactly the same in both cases. Exactly the same. There won't be any difference at all.
How about new?